Chapter 7 is going to be all about naming different types of chemical compounds. And these are all things we've done back in 9th grade. So, to review, a compound is when we have two or more elements that have been chemically combined. That means that they are bonded together. When this happens, the elements will lose their individual characteristics. So like when we have sodium coming together with chlorine to make sodium chloride, sodium is a soft white metal and chlorine is a green and toxic gas. And when they combined, they form a white, non-toxic crystal. So that's what I mean by they lose their characteristics, because the sodium is no longer a soft white metal, chlorine is no longer a toxic gas, and so they create something brand new. Lavoisier was the scientist that gets credited with developing this naming system. We call a naming system nomenclature. And so when we have this naming system, we look at two different types of chemistry, and their names of these chemical compounds are based on which type of chemistry they fall under. So we have organic chemistry and inorganic. Organic chemistry is the branch of chemistry that deals with compounds containing carbon, and inorganic chemistry deals with compounds that do not contain carbon. And so most of the ones we're going to look at today are going to be dealing with inorganic compounds. So there are a couple different types of formulas. We have molecular formulas and empirical formulas. Molecular formulas are chemical formulas that indicate how many of each type of atom that are present. So in the example here, we know that we have one nitrogen atom bonded to 3 hydrogen atoms. We're pretty familiar with the molecular formula. We use them quite regularly. The empirical formula is a chemical formula that shows elements in a compound at their lowest whole number ratio. So when we look at glucose is C6H12O6. This is not their empirical formula. This would be the molecular formula, because it tells us how many of each atom are present. Glucose's empirical formula would drop this down to carbon, hydrogen, to oxygen, because this one shows it in its lowest whole number ratio, because each of these is divisible by 6. So 6 divided by 6 gives us the 1, 12 divided by 6 gives us the 2 here, and then oxygen, 6 divided by 6 gives us the 1. But remember, we don't actually write the ones. And so that is what makes this the empirical formula. So many compounds will have an identical molecular and empirical formula, like our example up here. That is already in its lowest whole number ratio, so that works for both the molecular and empirical formula. Monatomic ions, mono for meaning one, mono, are ions that consist of a single or one atom with either a positive or negative charge. And we call these cations and anions. A cation forms when a metal atom loses an electron, and this happens for groups 1 through 3. The monatomic cations have the same name as their parent atom. And then our anions form when nonmetals gain electrons, and this will be in groups 15 through 17. And the anions will have the ending "ide." So, for example, chlorine becomes chloride. So cations and anions strive to have the electron configuration of noble gases. And so this will determine how many electrons they either gain or lose. So this table tells you some common monotonic ions. However, we use the periodic table to help with this. Elements in group 1 lose 1 electron, giving them a +1 charge. Group 2 loses 2 electrons, and group 3 loses 3 electrons, giving each element in those columns either the +1, +2, or +3 charge. Then we skip the carbon family, and then starting with the nitrogen family, they gain 3 electrons, giving them a -3 charge. Oxygen family gains 2 electrons, giving it a -2 charge. And then elements in the halogen family will gain 1 electron to get that noble gas configuration. And that gives them everything in that family a -1 charge. And you can see that up here in the table. So fluorine, chloride, bromine, and iodine, all of these elements get that -1 charge. So you won't see this table on any test or quiz because I will expect you to be able to pull the data from this table by looking at the periodic table. So you're going to have to remember the +1, +2, +3, skip, -3, -2, -1 pattern of cations and anions. So then the transition metals are capable of forming more than one type of stable ion. And so we use something called the stock naming system for these, and we use Roman numerals. Switch colors. And these Roman numerals are used to indicate the charge. There are 3 cations that do not use the stock naming system, and that will be silver, cadmium, and zinc. And this is because they only have one possible charge. And silver is always going to be a +1, cadmium will always be +2, and zinc will always be +2 as well. So make sure you commit these 3 rule breakers to memory. Another rule breaker here is mercury. Mercury 1, it has a pair of mercury atoms bonded together, which will give it an overall charge of +2, even though it's written as mercury 1. Then some clues. When you see words or element names that end in ic and us, it will tell you that ic is the ion with the higher charge and us will be the lower charge. So ferric versus ferrous, they're both iron ions, but ferric will be +3 and ferrous is +2. Now, you wouldn't know the actual numbers based off the name. All you would know is that the ic is going to have the higher number and the us will have the smaller number. You would just I happen to know that the 2 possible iron ions are either +3 or +2. And so that's all that you really get from the ic versus us, is that one is going to be higher than the other. So this table gives you some common transition metals. Again, I'm not probably going to be giving you this transition metal table because you can figure out the charges of these transition metals based on the anion that they are bonded to. So one thing that you should notice is that all of these transition metals, because they are metals, they are cations, which means that they all have some type of positive charge. So binary compounds are compounds made by combining a monatomic metal and a monatomic nonmetal. So remember, binary, bi means two. So if we have a mono plus a mono, 1 plus 1 gives us that 2. And so we're only going to have 2 elements in binary compounds. It's going to be 1 metal, and it can be a transition metal, and 1 nonmetal. Generally, the metal will be written before the nonmetal, and the subscripts do not affect the name, and the overall charge on that compound has to be 0. And so I think we're going to practice a couple of these here. And so with these, you're going to have a couple procedures, those of you that like steps. So the first step is to write the symbols of the elements. So we have cesium and fluorine. Then your second step is to write the charges. So that requires you to look at the periodic table. So you'll find cesium in the first column, so that gives it a +1. Fluorine is in the halogen, so that gives it a -1. So then your next step is to check or see if the charges equal 0. So in this case, we have a +1, -1, and that gives us a 0. And so if yes, slide symbols together. And that just means put them together and you're done. So we could practice our next one. Calcium and sulfur symbols, calcium Ca, sulfur S. Find them on the periodic table. Calcium is in that +2 column. Sulfur is in the -2 column. We can check that our charges, +2, -2, that equals 0. So we can go ahead and slide the symbols together. And we are done. So then we can keep practicing. We have aluminum and chlorine. Find their charges. Aluminum is in the +3 column over here, and chlorine is in that -1 column. Now when we check here, we have a +3 and a -1, and here we don't equal 0. So if we don't, then we need to deal with subscripts. And the subscripts are those smaller numbers. And generally speaking, what you can do is whatever this charge is will be the subscript that goes kitty corner. And whatever this charge is will be the subscript down here. Notice I did not write +3s or -1s. It's just the number that transfers down. And so when we do that, we can check, all right, so 3 positive charges times the 1 element gives us an overall +3 charge on aluminum. Here we have a -1 charge times -1 times the 3 chlorine elements for an overall charge of -3. So now we have a +3 -3, which gives us an overall charge of 0. Now that we have an overall charge of 0, we can slide the symbols together, but if you wrote any new subscripts, you have to carry those along, unless it was the 1, because we don't write the 1. So we can try this again. So we have zinc and nitrogen. So zinc falls in this transition metals. However, it was one of those rule breakers, that it only has one possible charge, and so that would be a +2. And then your nitrogen is up here in the -3 column. And when we check to see if those charges equal 0, we have +2 -3, and nope, that does not equal 0. So now we have to monkey around with the subscripts. And remember, do your diagonal trick. Zinc with a 2, so zinc's 2 transfers down to nitrogen. Nitrogen's 3 comes over to zinc. And then you check your math. We have an overall +2 charge on zinc times the 3 zinc atoms, which gives us an overall charge of +6. Checking nitrogen. Nitrogen has the -3 charge, and we've made it so there's 2 nitrogen atoms, giving it a -6 charge. So we have a +6 -6, we equal 0. So now we can write our elements with the subscripts we've added for our final answer. So make sure that you have this kind of step process memorized and ready to go. So when we are given the symbols and we have to go to the name, it's pretty much you just write the first element as is. You will have to note if it's a transition metal or not. And in this case, we do have a transition metal with silver. However, silver is one that does not use the stock naming system. So we can just call it silver. And then you write your second element. And since it's the anion, it gets that IDE ending, silver sulfide. So then we can move on to palladium oxide. So palladium. And palladium is here in the transition metals. And so you know that it's going to have a stock naming system. So we're going to have the parentheses that separate the two. And palladium oxide. To figure out the number that goes in here, you look at oxide's charge, which is a -2. So that means the charge on palladium, you have the charge on palladium -2 has to equal 0. So what minus a 2 will give you a 0? That would be a +2. So you write that, but you write it in Roman numerals. So another example, we can look at platinum. Platinum falls in your transition metals. So you put the parentheses, and then we have chlorine, but chlorine becomes chloride because it's an anion. And then chlorine has that -1 charge. But since we have 4 of them, our overall charge on chlorine in this compound is -4. So platinum's charge is a positive something. -4 has to equal 0. So in this case, since there's only 1, so plus something times the 1 platinum ion has to equal that +4. So our platinum charge is 4. And again, in Roman numerals. So then our last example, we have vanadium. Vanadium's a transition metal, and oxide again. So we look at the charge. Oxygen's a -2. So our overall charge with the oxygen's 5 atoms is a -10. Vanadium has a positive charge, and there's 2 of those atoms, and it has to equal that positive 10 so that we equal 0. And so we have to have 5, a plus 5 on that bandium. So we write that in the middle there. So that's your stock naming system. A couple elements that also use the stock naming system that don't fall in this transition metals would be tin, lead, and I believe antimony, which is SB. Ternary compounds are ionic compounds that are composed of 3 or more elements. And so this is when we start to talk about polyatomic ions. Polyatomic ions are ions composed of more than one atom. It will usually have endings 8 or ite, and there can have oxoanions, and this is when there are 2 common oxoanions for a particular element. The one with more oxygen atoms gets the 8 suffix, and the one with fewer oxygen atoms gets the ite. Again, this is like the ferric and ferrous. It doesn't tell you how many, it just tells you which one has more. So here is your common polyatomic ions. This is the chemistry version, so it will look a little different than the one we used in 9th grade, and you will get this on tests and quizzes. So this will be provided for you. And so we can practice naming these compounds. Again, your resources are going to be your periodic table as well as that common polyatomic ion sheet. So starting, we have NH4, and NH4 is a polyatomic, so we can call it ammonium. And then NO3 is also a polyatomic, and NO3 you can look up down here is nitrate, so it'll be ammonium nitrate. Here, our second example, we have Na2Cr2O7. Backing up. Ammonium and your mercury ions are your only positive polyatomics. Otherwise, your polyatomics are almost always anions and will be listed second in the naming. And so you can see here, we have just regular old sodium. And so you can look up the Cr2O7 in your polyatomic chart, and you would see it's right here. So it'll be oxalate. Notice that sodium is not a transition metal, so we don't need to worry about the stock naming system. So then our next example, we have lead. Lead is one of those that is technically not a transition metal, but it still does the stock naming system. And then we can look for CO3 in the chart. And here's the CO3 carbonate. And so the important part here is we need to know carbonate's charge is a -2. So that means our charge on lead has to be the +2 in order to get it to balance out. Our last example here is magnesium. Magnesium is not a transition metal and does not use the stock naming system, so we don't need to worry about the parentheses and the Roman numerals. And then we look up our polyatomic in our chart, which is up here. And so we would have magnesium acetate. So that's how we name these compounds. When you use the polyatomics, you have to just pull the exact name off the chart. Now, if we go the opposite direction, we're given the names, but we have to write it in the symbols. We use the system that I gave you on the earlier slides, where you start with writing the symbols, potassium, and then you look up hydrogen sulfide. Here is HS. Then we deal with the charges. Potassium is on our periodic table with a +1. The charge, we look on the table here, is a -1. That happens to equal 0 already for us. +1 -1 equals 0. And so then we can just slide the symbols together for our final answer. So moving on to our next example, we have iron and oxalate. And oxalate from the table is C2O4. Our next step is to write the charges. This gives us iron's charge, will be a +3. Oxalate from the table is right here, a -2. And so we do our diagonals, and the 2 comes down here. And since we have to add a subscript to this polyatomic, you have to put it in parentheses and place the subscript on the outside of the parentheses. So our final answer here is Fe2 parentheses C2O4 and then our subscript 3. Another example, moving on, we have sodium. Peroxide is O2 from the table. Then your charges, sodium from the periodic table is +1. Peroxide from your polyatomics is a -2. And so we put our subscripts down, do the diagonals, and we can then say, all right, Na2 and O2, we don't need to write this 1, so we don't have to worry about the parentheses. Last example is tin, Sn, and chromate, CrO4. So chromate is right here. Our charges, tin tells us right here, so +4. Chromate is a -2, so we do the diagonals. And when we do that, we get tin 2 and chromate 4. But what you have to check here now is we're not in our lowest whole number ratio. So to do that, we have to just divide out the 2. So it'd be tin and then chromate, CrO4, 2. So these each get divided by 2 for our final answer. So a couple things to remember as you go through these problems. Everything needs to balance out to 0 charge overall. You need to watch out for your transition metals and your stock naming system. And your final answer absolutely has to be in its lowest terms. If you're looking at this one right now and going, well, this isn't in our lowest terms, we have to keep this as Na2O2 because of it being peroxide. If we were to change it, it wouldn't be peroxide anymore. And so just be careful that there's always an exception to these rules.